This is the ROS Developers Podcast, episode 76.
The ROS Developers Podcast, the ROS Developers. The ROS Developers Podcast, the ROS Developers.
Hello, ROS developers, and welcome to the ROS Developers Podcast, the podcast that give you insights from the experts about how to program your robots with ROS. I am Ricardo Tellez from The Construct, and I would like to dedicate this episode of today to all those people that are thinking about moving their robots to ROS2. So when you try to do that, one of the problems to move to ROS2, it was the lack of a stable navigation system for ROS2 robots. But as you will learn today, this problem has been solved. So if you want to move to ROS2 and want to try to make a robot navigate, then this episode is dedicated to you. Because today we are going to talk about the ROS2 Navigation Stack, which allows ROS2 robots to navigate autonomously. But before going into that, let me remind you about our ROS Online Academy. Yes, at The Construct, we have created our online academy named the Robot Ignite Academy, which is an academy that contains a ROS learning path for beginners. We start by teaching you Linux and Python for robotics, and then we continue teaching you all the basics ROS concepts required to become a master of ROS. Then we conclude with a course that teaches you how to build your own robot and how to ROSify it, including adding ROS control and so. So it's if you are interested to become a ROS developer, I will suggest you that you have a look at those courses and our online academy. And now is time that we go to our subject of today, of the podcast of today. So let me introduce you Steve Macenski. Steve works for Samsung Research America, and there he is the open source robotics engineering lead of the company. He is also a member of the board of the ROS2 Technical Steering Committee, and also is a maintainer and ROS developer of many important ROS2 packages related to the navigation system in ROS2. By the way, this is the second time that Steve comes to the podcast. And also would like to say that Steve was the winner of the ROS Award 2020 as the best ROS developer of the world. So congratulations for this award and welcome to the podcast, Steve.
Hi, thanks. Great to be here. Yeah, actually, during the introduction, looked at the timestamp. I think the original one we did was number 56. This is 20 podcasts later, so great to be back.
Okay. I didn't check the previous number, but it was we were talking about the SLAM toolbox, also some packages for navigation for ROS1 that you created also.
Yeah, and that's all ported over to ROS2 now, so if you didn't check out that podcast, you should. And all of that stuff is now true with ROS2 as well. It's fully ported and available in all of the current ROS2 distributions.
Great, super cool. Then I will put a link to the SLAM toolbox in the show notes also of this podcast, and also a link to the previous interview. So maybe it's better that you start with that previous interview, so you will understand better what we are going to talk today here. And I would like to start by, if you can explain to the audience, so what is the ROS2 navigation stack and what is the functionality that is included in it?
Yeah, I generally like to start most things when I talk with just kind of a very basic overview of like what is the problem we're trying to solve. I find that the level of knowledge that different people have is very different. So maybe some very senior people view this as a problem in one domain, and very junior people maybe think that other problems are in this domain. So I just want to kind of clarify a bit of what is a navigation system or a navigation framework.
Okay.
And then the navigation stack is then a more ROS specific use of words. Back when ROS used to have stacks and meta packages, that made a lot more sense. These days, it's more just about a single repo with a bunch of different packages in it. But a navigation system, kind of the goal of this is to take your robot and go to a specific location. So the role of the navigation stack is not to tell the robot where it needs to be going. It just says, okay, I now have this command from my autonomy system to say, I need to go to this position, or I need to go to this pose, or I need to go through this via point at this velocity. So it's dealing with all the problems around the task of how do I go from point A to point B. And so that can include perception, so processing cameras, LiDARs, 3D LiDARs, radars, sonars, IR sensors, all these great sensors that we have available to us now, and creating some sort of environmental representation of the world. And that's where we're going to be creating our plans through a path planner, and then creating valid motions through a local trajectory planner. So those are the kind of the main points that a navigation system has to accomplish, and then doing so in a very safe and reliable way. And that's essentially what the navigation stack does. Is it provides this cost map representation of the world currently. It also provides some basic planning algorithms, some basic local trajectory planning algorithms, and recovery systems, so that if your navigation stack gets into some trouble, it can get itself out of that trouble. And then finally, a localization method called AMCL, which I don't necessarily think is belonging to the navigation stack. I think of that as just sitting in the same repo for historical reasons, but I don't think that the positioning problem falls under the navigation problem.
Why not?
It's more of an input. So if you have a navigation stack and you're trying to go from point A to point B, the where am I problem of this is kind of just naturally decoupled. So in ROS, we have this decoupled methods through TF. TF really helps us with this. So AMCL or Orb Slam or Slam Toolbox or whatever Slam or localization system you'd like to be using, really all it needs to be producing is just this map to ODOM transformation. And after that, it's the navigation system will work by itself. So I kind of view this as a cursory input through the TF system, and not something that you should think about as a navigation problem. The field of SLAM and localization by itself is quite challenging, separate of the challenging problems in the navigation community. So at least for me, it's easier to separate these two ideas.
Yeah, makes perfect sense. Never thought about that, and now that you mentioned that, it makes perfect sense. Yeah. Okay, so from all those systems that are required to do the navigation, which ones are already integrated into the ROS2 navigation system?
Yeah, so all of those parts.
All of
I don't
them.
think you can have you can't have a full navigation system without having all of those components. If you can't have a global planner, then you don't know where it is you're going in global space. You don't have a local planner, then you can't follow that path or avoid obstacles. You don't have a cost map, then you can't see the world to actually plan or control in. So really, you need all of these components to build a navigation system.
Great. That means that now we can have a ROS2 based robot that can navigate completely. So all the elements of the navigation stack are already present. Okay, so I mean, I want to point this because it's such an event for me in ROS2. It's a very important point because lacking all those functionality was one of the complaints of people about moving into ROS2. And
we've had that capability in the ROS2 navigation stack for about a year now, but I'll say that it wasn't necessarily as reliable as we liked. There were a variety of issues at the RCL CBP client library level and below. There were also some things we were working through to reformulate the framework. So rather than having move base, which is this single process with a bunch of stuff going on that you can't really reconfigure, and then you're also having all this stuff in a single core, create some issues for us. So we spent a lot of time redesigning the system, not just a straight port from ROS1. So now we have separate action servers for all these main components. So the local trajectory planner is a different action server than the global planner, which is a different action server from the recovery servers. And then all of those things can be run on different cores or even different machines, or all in the same core, same machine with component lifecycle nodes. We're also using lifecycle nodes, which help a lot with reliability. We've done a great deal of work profiling the CPU and trying to find issues. there's a number of major improvements that we've made on top of the ROS1 navigation stack. So in my mind, this is kind of a new navigation system separate of the ROS1 navigation stack, where we built on the heritage of 10 years of knowledge from the original navigation stack. And this is currently the culmination of that effort.
Okay, so it inherits, let's say, the functionality because it has the mapping, the map planning, and all that recovery behaviors, but the implementations is being done in a completely different way. So you mentioned that it doesn't exist anymore, the move base.
Yeah. So MoveBase no longer exists. That's replaced with what we call is the BT Navigator, where BT stands for behavior tree. We've separated, instead of using the state machines that MoveBase was to control the different components of the navigation system. So, for instance, the update planner or update controller rate, the replanning rate, maybe the cost map update rates, were all being controlled by this one central C++ hard-coded item, which had a variety of different plugins and different parameters you could set. But at the end of the day, the logic was set in the code. Now we're using behavior trees, which are well used in the AI and video game industry, graphics industries, these kinds of places, and have really started to bleed into the robotics industry in the last 5 years or so. So behavior trees have a benefit of being able to be runtime reconfigurable. There are some state machine libraries that also do this, but pretty much every behavior tree library will do it. And you can create these little primitive things. So you want to say, call the controller, or call the planner, or call the elevator API to summon an elevator or something. And then you can create this tree structure to have your autonomy application or create a navigation behavior that's optimal for your use case. So for instance, we can have a tree structure where the one of the main branches on that tree can be trying to do the planning control tasks, and if those tasks fail, they can go into another subtree of that behavior tree and execute a bunch of different recovery behaviors where we check certain conditions before we trigger each given recovery. So it's not just knocking them down in order, saying, okay, you clear cost maps, then you spin, then you back up. Now you can say, oh, am I stuck? Okay, therefore I should back up. Or if this particular failure mode occurred, given some information on the blackboard of the behavior tree, therefore we do this particular recovery behavior. So you have a lot of more context that you have available to you, and you don't have to design all these different state machine transitions, which can become quite complicated and really intractable if you're trying to have a navigation system with many different algorithms or many different planner implementations or many different recovery modes.
Okay, then if we start with the basic ROS2 navigation stack, and then we already have some behavior trees for the recovery behaviors already implemented, right?
Yeah, we currently have, I believe, 4 or 5 different behavior trees you can select from. The default one, I think, is the best of those. And the default behavior tree essentially is going to be doing the planning and controlling like you expect. So it's going to be calling the planner at a given replanning rate. And then that's going to call the planner server to actually compute a plan and return that back to the behavior tree to give to the controller server. And the controller server actually spins its own threads, so it actually will do the while true essentially for computing the new local trajectory plans based on cost mode updates and the new plans. But then we're just sending the new plans to that controller through the behavior tree framework. And if each of those two things have then separate trees associated with them, so if the particular planner fails, we have planner-specific recovery behaviors that will be triggered. If the controller fails, we have controller-specific recovery behaviors that will trigger. And then it will attempt to replan and recontrol and see if that fixes the problem. After a certain number of retries of that process, it'll then enter what I referred to as the recovery subtree. And that recovery subtree is just full of a bunch of different recovery behaviors that we have access to that we built for the ROS2 navigation stack. I'll admit some of these recovery behaviors are fairly basic. Things like spinning, things like backing up, clearing cost maps. It's really hard to build general purpose recovery behaviors. Everyone's robot is different and everyone's environment is different. Some people backing up makes a lot of sense. Some people going forward makes a lot of sense, or going to the left makes some sense. Potentially, if you want to call for help, you can easily make a recovery plugin that will call some SMS API or call your operator system to say, hey, maybe you should give this robot some attention. These are all really trivial. Then you can just stick that in your behavior tree, and it should call you when it has a problem, essentially.
Wow, that's cool. So if you have a humanoid robot, then it can raise its hand and say, "Hey, please help," like this. So you can integrate
yeah, exactly. Yeah, no, and I think this is really great for mood-based flex. And David Liu, with his work with DWB, talked a lot about contextual recoveries, and they did so by throwing particular exceptions at particular places will cause particular behaviors. But instead, we're doing this through all of this is reconfigurable through the behavior tree itself. So calling for help, I imagine, is something that most professional robotics users are going to be implementing. There's clearly many different ways that can be done, so it doesn't really make a lot of sense for me to support any particular way of doing that, since there are a variety of different operating services or custom operating services. Some of the examples of things you could add in there as well are things like elevator APIs. If you have a robot and you want to go in an elevator, you say, go to this staging point, and then in the behavior tree, say, am I at staging point and should I be going upstairs? Then call the elevator. And that all can be done through this behavior tree API very trivially. You can also do things like opening automatic doors. I know in the context of hospitals where a robot might need to get through a security door for an emergency room, that you can call the APIs to these doors for the infrastructure. Really, the list of things you can do here is endless.
Yes, so it opens a new list of possibilities for just for navigation. So it's amazing. Then we'd like to ask you about the mapping algorithm, which is included in the ROS2 Navigation Stack. So, but based on your previous answer, I'm not sure right now if you are considering mapping as a skill of navigation.
No, yeah, I definitely don't consider mapping to be a skill of navigation.
Okay.
I consider it to be a completely different field. That's just a cursory. If you think of your black box of a system diagram, the navigation black box and the mapping and localization black box are two different black boxes. But with that said, we can't just ignore that field for the ROS2 navigation stack or in ROS2 in general, right? We need to have some support for some workhorse SLAM implementations and library. 2D laser scanning SLAM is actually SLAM Toolbox, which is what we talked about a year ago, I think, on this podcast, and talked about it at ROSCON.
Okay, so let me ask you about the localization algorithm that is being used for doing the localization of the robot in ROS2. Is it still being used, the AMCL in ROS2? I'm very interested to know this answer because we are thinking about moving into ROS2 and using the navigation system, but we always come from the original ROS navigation stack of ROS1. That's why it's kind of we try to make the equivalent from one side to the other, so it's easier for us to understand. So that's why of my question. So are we still using AMCL in ROS2 navigation stack?
Yeah, so we're still using AMCL. It's not, in my opinion, long for this world.
Okay.
But so AMCL was one of the very few packages that was just a straight port from ROS1. So that and CostMap 2D, I think, were the only two packages that we just straight ported over to Navigation 2. So it's pretty much the same code. I think we refactored it a little bit as we were trying to make some plugin interfaces for the different motion models. That didn't quite get completed. But overall, AMCL has basically not changed at all from ROS1 to ROS2. That's not something that we're necessarily very happy about. That's been one of the major complaints within ROS1 for many years now. That people are losing localization or it's not working as expected. Just a variety of different issues, and the code base is very complicated. It was pulled out of Stage, I believe, a very long time ago, and it wasn't necessarily refactored to live in the navigation stack long term. So it's very hard to modify. There are some inline comments which does help you kind of figure out what's going on where. But I will say, if you're trying to modify things, it's very hard to merge those pull requests because just it's so complicated to kind of understand the framework and what that change might impact on other users. So we are putting a great deal of time into figuring out what is the next 2D LiDAR based localization solution that we want to be supporting. Long term, I don't think that's going to be AMCL. AMCL is not going to be going anywhere. It might move into another repo, but it'll still be supported for the long term, at least until we have another alternative for it that we can prove is better in many regards. So because some of the work that we're doing on that is for a NDT MCL implementation. And those who do autonomous driving things or are familiar with 3D LiDARs are going to know NDT very well as being kind of the basis of many different SLAM and localization implementations in that ecosystem. But we're starting to pull some of that work back into the robotics space. So typically things like AutoWare do NDT mapping. And so what it's essentially doing is just directly doing an NDT scan match against an existing 3D point cloud map. And then that's giving them this positioning information, and they might filter this through something like robot localization to smooth out any sort of perturbations or variations. For the mobile robotics use case, that doesn't necessarily work very well because we don't have the kind of visibility that a 3D 3D laser scanner mounted on top of a car has, right? You can see 100 meters in every direction. Wow. You have very rich texture from buildings. If you're in a downtown environment, you have GPS information that's giving you very good positioning estimates. You don't get print any of that in the mobile robotics use case, right? Most 3D LiDARs are mounted fairly close to the ground, are only going to be seeing, maybe forward and backwards a large variation of meters, but then on laterally, if you're in an IL space, you might only get like 10 meters wide or something. So we need to be more probabilistically complete so that we're not just doing direct matches and saying, kind of word of God, this is where I am. And so that's where the NDT MCL implementation comes in. So we're still using an MCL as the backend structure of the mapping algorithm so that we're able to get some more accuracy there. And when reviewing research papers of potential solutions to replace AMCL with, I was quite impressed by the resolution to localization quality metrics of NDT MCL. It almost looks as if we can increase our base mapping resolution to be much much lower resolution. So rather than having maybe a 5 centimeter pixels, they could be potentially 15 centimeter pixels and still get better localization quality, which might be beneficial for very large environments where we have very large maps, lowering the memory utilization. And I'm happy to say we're doing some work on this, and we should have something hopefully before the end of the year.
Wow, nice, amazing. Waiting for seeing this release, and maybe we can talk also in another podcast about this release. You mentioned that it's called NDT and AMCL.
No, just NDT MCL.
MCL, okay, just without the A with
so it's just a Monte Carlo localizer. So the A is adaptive. And that's a specific variation on that's used by the navigation stack.
Okay. Then you mentioned about the localization algorithms, and now what about the algorithms used in the ROS2 Navigation Stack for path planning and control? So have they been changed from the ones that we were using on ROS1?
Yeah, they've changed a bit. So not as much as we'd like, but it's something where we focused far more on the framework and stability and reliability first before kind of going into replacing a bunch of the algorithms. So in terms of path planning, the major supported path planner is still NavFN, which is a wavefront-based Dijkstra's and A-star planner. Then for the local trajectory planner, we have DWB, which is David Liu's our new version of the DWA, which is a dynamic window approach local trajectory planner. It has many of the same features of DWA, and if you like DWA, there's even a way to configure it to act like DWA. But DWB is a more flexible version of that, so you can have a lot more different critics and a lot more different trajectory optimizers. There's a bunch of different plugin interfaces that you can implement to create very custom behavior to be, anything between really dynamic obstacle avoidance to really strict path following, and anything in between. There's a lot of variation that you can do there. It is very sensitive to gain tuning, just like DWA was, so it will require a little bit of effort on the user's side to tune this to be adequate for their platform.
Okay, and do they have also a super long list of parameters to be configured in order to make it work?
Yeah. I am very against hard-coded values. So there's always lots more parameters than I expect anybody to ever modify. But hopefully, just find the ones that are important. But we do try to do that a little bit. The Navigation 2 parameter file set that we have in the Nav2 bring up package is tuned specifically for the Turtlebot 3 platform, but are good for most small hobby platforms or whatever. But we do try to make it so that the important parameters are set out in that YAML file, so that if you're modifying things, you should be able to, the 80-20 rule, you should get 80% of the capabilities modifying those 20% of parameters. But the full list of parameters are far longer, and that's actually been a big push of mine in the last year or so is documentation. So we have this Read the Docs website that's navigation.ros.org. And I've put a lot of time on weekends and in evenings building a lot of tutorials, getting started guides, install guides, parameter description files with all the defaults, all the types for every single parameter in the entire stack. There's getting involved instructions, pull requests, templates, things like that. And we're constantly building more and more of this documentation.
Amazing. That's a very important point, because the people doesn't understand what those parameters are, because they are just users, right? And then they need to figure out a place where they can have some explanation. So if you are already providing that, it's going to help a lot on people adopting
definitely.
this framework. Great.
And we also have a list of those, all the plugins that are available as well with the navigation stack. So there's a bunch of plugins and different packages all over the place. So there's a specific web page on that contains an exhaustive list of high quality known plugins for all the different interfaces. So for all the behavior tree plugins that we have available, there's a list and a description and authors for all the different planners that are available both in the stack and in the community. Those are all listed there as well. All the different cost map plugins, all that kind of good stuff.
Okay, and you mentioned right now about the plugins. What are the plugins used for? So what do we implement in those plugins?
So like different algorithms. So if you're in the planner server, then you might have a planner plugin which implements a global planning or a Keynote dynamic planner, or whatever is interesting to you. Then we have the controller server, which hosts 3 different plugins. It hosts the controller plugin, which is the local trajectory planner. So that's something like a TEB local planner or a Care follower or GWV or what have you. Then there's also a progress checker. That is the goal of the progress checker is to tell the controller server whether or not progress is being made towards the goal. And you can set that to say, if we don't make progress within a couple of minutes or within a couple of seconds or whatever metrics you're interested in, then, fail the navigation task, because clearly we're in a bad situation. So that's a plugin interface. The basic implementation of that is just checking the distance and angular rotations over some local time horizon. And if the robot stops to make progress for some period of time, then it will fail. We also then have another plugin in there that's the goal checker, and that's the goal of that is to tell the user or tell the navigation system whether or not it's actually met the goal that's been trying to create local trajectory plans towards. So the basic implementation of that is just going to be checking the pose of the robot, so the position and orientation, and checking that's within some threshold set by parameter systems, and then it will return true or false if it's within that to end the navigation task as successful. Then we have the cost maps. So the cost maps have two sets of plugins now. So there's the cost map layers, which are just different algorithms for processing data or maps or whatever inputs that you find interesting, and marking those obstacles or unknown or free space within the cost map, so that you can navigate within some dynamic environment or some very large environment, or whatever space you're navigating within. Then there's a second set of plugins that we're currently reviewing in a pull request that are going to be merged fairly soon here, that we refer to as cost map filters. And the idea of this is filters on the cost map that should not affect the cost map itself. So if you have something like a keep out space where you're not really processing data to say that, oh, there's an obstacle there, you really shouldn't be there. It's more of taking a mask of space where you can be, and a mask of space where you can't be, and then telling the robot that, okay, you can't plan in this space, or you can't generate valid control efforts in this space, so that the robot doesn't go there.
Oh, that's cool.
Then the other kind of base implementation that we're providing there is a speed restricted zones layer, which is another common request with users, is to be able to say, within this space, I
Area.
want my maximum speed to be X, and within that space, I want my maximum speed to be Y.
Wow,
And so it
that's
allows
super
the
cool.
user to create a mask of speeds that you want to use. And then, as long as your local trajectory planner takes in these parameters it's resetting as it moves between zones, then you should be good to go.
Oh, that's an exhaustive list of all the plugins that you guys can use.
Yeah,
on
I think there's
the
actually a
ROS.
couple more. Those are just the ones that
Okay,
I play with
it's-
most often.
Okay, still not exhaustive.
No, yeah,
Okay.
no. Also, so I won't go too much into it, but the NDT MCL implementation actually is going to be a framework. So we're actually building plug-and-lib interfaces for most of the major components of localization SLAM. So like an extended Kalman filter would be a structure plugin, as well as the MCL. But then also then the scan matcher, the NDT scan matcher itself, that could be a plugin for a different type
Wow.
of scan matcher or a different type of structure. And so we have a bunch of these different plugins within there, so you can mix and match between different like matchers or backends or graph optimizers or whatever you care about. I think there's always a joke where the junior engineers build implementations and the senior engineers build frameworks. And so this is definitely in that category where we're building a lot of frameworks.
Okay, that's very cool. So then in that last case that you mentioned about the plugins for the NDT MCL, then you can concentrate on optimizing just the part of the localization system that you are interested by plugging those your own implementations, the ones that you're interested, and that makes the whole system a lot more flexible because you don't need
Yeah,
to
exactly. Yeah, it's always very frustrating when you want to just test out. Maybe you're an academic and you just want to test out this new method for matching point clouds. And you want to see if you can build a better SLAM system in the state of the art. Right now, you'd have to either fork something that's open source,
build
if there
everything.
even is an open source that's something close to what you want to do, to modify it for your use cases, which I don't even, that's not a very common case at all, because so few of these novel papers have implementations associated with them in open source. So what you end up having to do is re-implementing the entire thing, and then you end up with a bunch of these just very bespoke implementations of things which might not be optimized or might not even actually work, or might have these horrible bugs. Or in the case of like Orb Slam, where it's a really good piece of software, but it's really not very well structured and it's hard to modify. And so the goal is to have a framework that can be used where if you want to build a new version of a Slam implementation that still runs on an MCL, well, poof, you just already have an MCL plugin available to you. It's already been well tested. It's been documented. It's well understood. And then now you just need to implement your new, whatever matcher or, whatever is interesting to you.
Your filter, and then you can compare with the results of others in a very systematic way.
Yeah. You just switch which plugin you load for your front end, and then you run the same data set over again. You should have some results, and it's not a result of performance issues between one implementation to another, because you're working with the same backend for all of them. And so any sort of poor implementations or good implementations aren't going to be modifying your results significantly.
Great, that's an awesome idea. Very, very cool. Very cool. I had no idea that was implemented inside the ROS2 Navigation Stack.
Well, it's something we're working on.
Yeah?
There's a lot of ongoing projects.
Oh, yeah, okay. Wow, that's amazing, the job that you're doing there. Really, really impressive. So let me tell you, well deserved the award for the best ROS developers. best deserved.
Well, honestly, this a lot of this came is actually just very, very good timing, I suppose. So when COVID-19 hit, and clearly COVID is not a good thing, and I'm not proposing that it is, but it resulted in a number of high quality PhD students and undergraduates who would have had internships in the Bay Area or at wherever they would be interning. And those internships were largely canceled because of the just not knowing if people could go back to work, or not knowing where the next revenue is coming from. And so there are a large number of just really interested students that just wanted to get involved and learn some skills. And as part of this summer, I've actually been mentoring a few dozen students, and we have very lively Slack channel that we chat on. And a lot of this work is a result of collaborations with them, where I kind of have a vision and we work through some design, and they do the by far the heavy lifting, actually implementing things. And it's been a really great arrangement. And I hope that as the summer kind of close to a draw, that either next summer we can continue this kind of development, or potentially continue during the school year. I've been in contact with a few graduate departments asking about potentially collaborating with professors so that as they're getting these master's students, kind of like figuring out what projects might be in their research interests, but also then in the open source interests, and seeing if there's some opportunity to have some cross-discipline collaboration.
Wow, super cool. Super cool. Very good. So eager to see what is resulting from that. Very cool. Then let me tell you one question. What is the advantage of having all the navigation components as runtime configurable? And actually, what does it mean to be runtime configurable?
Yeah. And forgive my language. My language here is incorrect. This is not an area I often play with. But so I think when we talk about plugins, that they're dynamically loaded shared libraries. Mm-hmm. I think that's the technical phrase for it. So you have these, in CMake, you have these, you're on CMake and your package, and poof, you have these SO files. And essentially, what's doing is coordinating between where are these libraries and what are these strings called when we want to load one. And so what's happening is then I want to load my STVL plugin. It's going to look up into some database and say, okay, this shared object file, this is going to be your STVL plugin. It's going to load the shared object library and then put it as a base pointer to the derived class. And so it end up just acting like if you were to have the basic inheritance kind of structure where you have a base pointer to the derived class. And then you can interact with all the different APIs that you have through the base pointer interfaces. So one of the in my opinion, the most powerful reason to do this is separations of concerns. So the types of engineers that play with frameworks are very infrequently the types of engineers that also play with research designed algorithms. So I would like to make it so that the research focused algorithm designers, when they say, okay, I want to build a new trajectory planner, I want to build a new perception algorithm, I really don't want them to care too much about ROS. I don't really want them to care too much about navigation. I don't really want them to care too much about software engineering as an entire discipline. They should not have to care. Yeah. They just should have to say, here's this header that has these functions I must implement them. Okay. And then, there's some other stuff you have to do for the registration for the plugin lib library to find them. But, that's all pretty minimal. And then you now have the ability to have your really experienced software engineers playing in software land, and then you have your really experienced researchers playing in research land. Mm-hmm. And while they have to interact to create these interfaces, they're not being bogged down by each other's stuff constantly, which is, I think, a problem with other design patterns. So another way you could do things within ROS2 is using component nodes, which is analog to nodelets in ROS1, where you have multiple of these nodes in the same process. And that's commonly something I get questions about is, why aren't plugins just components? And my main answer to that is a separation of concerns. I don't want my algorithm designers to have to know anything about ROS2 or have to deal with building these frameworks or understanding how the ROS2 system is working. I want them to just be able to say, here's some inputs, give me an output, and that's all they have to do. And so I find that to be the best way to handle algorithms. I'm not sure I would use plugin lib for other software components if you want them to interact with each other, but if you're trying to separate out algorithms from a framework, I believe that's the best way.
Okay, so you are separating the specialization in some tasks, like could be planning, could be localization, could be whatever, and removing the burden to have to interact with the actual, how to capture the data from the sensors or from the ROS system. So those researchers, those specialists, people in those subjects, they can concentrate on implementing the best algorithm just for that task.
Yeah, exactly. Okay. And then if you have companies that want to have a very specialized vehicle, or they want different algorithms than what we supply in the default stack, then all they're doing is just building a new plugin, and then they can keep that closed source proprietary, and they don't have to fork the navigation stack to manually modify it, because they're just loaded at runtime through a parameter, which then makes it so there's less of these kind of closed source forks of the navigation stack where they, it kind of goes there and then never comes back out because they make enough modifications for their custom use cases that they can never really open source it again. So this makes it so they can have their own separate algorithms they need to, But then hopefully, my hope is at least that then if they're modifying the actual frameworks, that they're giving that back, because the framework isn't where their secret sauce is, right? Their secret sauce is in that algorithm. And so hopefully they give back when they make framework modifications and updates, so they can continue to receive the most latest and greatest framework as we keep developing more and more capabilities within the stack.
Very cool. Very cool idea. Also allowing companies also to make business and to contribute on that without having to modify the whole framework. And now that you mentioned that about modifying the algorithms for without modifying the framework, so what about the navigation system when it is not being applied to a round shape differential drive with wheels on the center type of robots? You know, that the ones that maybe they have the wheels on the top? That was a usual complaint in ROS1 Navigation Stack. So how does it works better in ROS2 Navigation Stack?
Yeah, it's almost like you've talked to me before. yeah. This is a big point I often bring up is, you know, I'm frustrated at the state of the navigation stack with ROS1, because it really only works effectively on these, you know, circular differential drive round robots on a planar surface. You know, while that's an extreme generalization, it does work on other robots as well. But that's kind of the de facto use case for it. So, you know, I think the best way to kind of talk about this is to break it down kind of one set of requirements at a time. So if we're talking about differential drive, it only works with differential drive robots. It also works with Ackermann steering robots. It also works on omnidirectional robots. The local trajectory planner and the global planner are actually more suited towards omnidirectional robots. So that support's already kind of there, baked in easily. For differential drive, DWB can be also tuned to work on differential drive robots. Obviously, given Locus Robotics has differential drive robots as their professional platform. But the global planner, NavFN, actually only builds omnidirectional A-star based plans or Dijkstra's based plans. So the robot would have to turn in place potentially to move to a different heading before continuing in its on its path that it wanted to. But that's not generally an issue that we have. You know, right? Different drive robots can generally spin around, so it's not a big deal. But then the other large class of types of robots are then these Ackermann steering car-like robots, and those. Yeah, and those are definitely an issue where people have identified that it does not work very well with the original navigation stack. So the planning assumes you have this little particle robot in particle space, and so you know you're going from one grid cell to another, and you assume that you can just do that and that's all fine. But with the constraints on an Ackermann steering vehicle, that's not always possible. You can't just make a 90-degree right turn in a narrow aisleway potentially. If your car is small, like if you have an RC car in an apartment or an RC car on the street or something, that's not a problem, because you can effectively treat your robot like a particle, because the space around it is so much larger than what you're trying to interact with. It should be fine. But then if you're in areas where the relative vehicle size is large, the relative environment size, so if you have a forklift in a very narrow aisleway, that is very different. You need to be taking into account not only the XY coordinates, but the XY yaw components. And that's the SET or SE2 subspace. So we need to be having planners that interact with that. And so there's work happening right now for a hybrid A-star planner, which is built specifically for the DARPA Urban Challenge. So that's built for specifically Ackermann steering like cars, with motion models that you can replace to use with differential drive or omnidirectional or whatever. So it's still going to be very, very flexible. And then OMPL-based planners, which are going to be using the Reed-Shep curves and all the different, I think Balk Mason curves, but that's more differential drive, using different classes of curves in a sampling space, so that we can actually enable on the planning side at least control over SE2 specific vehicles. Then your problem is then local trajectory planning. That DWB might not be your right option. The curvatures that makes are special to differential drive and omnidirectional platforms. But generally speaking, it should work on Ackermann steering vehicles. But generally speaking, isn't good enough for most of us. So let's not talk about that. So the TEB local planner, however, was ported to ROS2 and fully available with Ackermann steering support built into that. So that there are different parameters you can set to have an Ackermann steering car. And that's been shown to work on things that are fairly large, like a forklift. I'm not sure. There are some simplifications made to it that I don't think make it suitable for a literal like car. So I would not put it on my SUV, for instance. That I might want a different implementation for. But for things of a forklift size, roughly speaking, and smaller, like a Gator or something, if you have like an ATV, that would be fine as well. You can run Ackermann stealing vehicles using the TEB local planner. Okay. So that kind of covers the drivetrain side of things.
Yes,
yeah.
For the most common types of robots. Yes, that's very cool. For the cat-likes ones, the Ackermann one, we have a lot of requests also in our academy about how to program those in ROS1, in the navigation system. So it's cool to know that with the TEB planner, the TEB planner, so they can make the day, so they can use it and make it work like this. Because it's the one that we are teaching actually also in ROS1 for car-like ones. Yeah. Great.
So then,
sorry.
So, but in terms of some of your other requirements, I'll go faster on these ones.
Sure.
So you're saying like circular robots. This only works with circular robots. I would say that's not always true. It is kind of true, right? When we're talking about NavFN, where we're just talking about particle planning, right? If your robot is a circle that you can treat as a particle, that certainly makes your life a lot easier. But then also if you have square robots or things that are roughly speaking circular-ish, uniform in both axes, those already work fairly well as is. Your inflation radiuses might have some clipping of the corners, but hopefully your local trajectory planners are handling not just the XY positions, but also checking your footprint for collisions, and then you shouldn't have too much of an issue there. But really where you have problems is when you have very long vehicles or very wide vehicles or things where it's not uniform in both XY axes in terms of size. So things like I'm trying to think like the FarmWise tractor kind of thing. It's very long and not necessarily that wide. Things like that might have some problems currently in Navigation Stack, because if you're only doing this like particle checking at the center point, then you have to have your inflation radiuses set at the maximum diagonal length of the robot, so you don't collide with anything at any point at all. So what really needs to be done is using path planners that are not just checking the center point like NavFN is, but also checking then the extents of the footprint that don't go in collision. So you can only set the inflation radius to be the minimum radius of the robot, not the maximum radius, so you can get in those tight areas. And that should be taken care of with the OMPL and the hybrid A-star planners when those are complete.
Okay. Wow, a lot to test. So we have a lot of work to do to test all that and see how it behaves.
Yeah, the big things are just finishing these at least one of these new planners. So the local trajectory planners that are available can support all of these different classes. It's really just making available a global planner that also supports them as well.
Okay, I want to ask you now about this paper that you have recently published at ROS, which is about the marathon experiment using the ROS2 Navigation Stack. So can you explain to the audience the experiment and why did you decide to implement it?
Yeah, so me, Francisco, and Ruffin were working on this experiment and paper. So kind of the goal of this was to be a nod to the original Navigation Stack introduction paper, which was doing an experiment that they referred to as the office marathon, where they had a robot go around an office space autonomously and navigate for the duration of the marathon. And as the robot needed to be charged, I think it would email somebody or text somebody to, it would go back to the charging area and ask somebody to plug it back in. And it was a great demonstration for the original Navigation Stack to show that this is a working navigation system, and it was one of the first open source and high quality. Actually, I don't know if there were any other open source ones at that point. I don't know, whatever. It was one of the first I'm aware of open source implementations of a navigation system that were available. And it's been cited something like 500 times. It's been a fairly influential paper in the community, and so we want to give kind of a nod to that, and we wanted to figure out what is the next kind of like transition we can do on top of this. So rather than doing one marathon duration, we attempted to do 2 marathon durations. We stopped a little short of that, I believe. We didn't quite get to 2, but we made a good attempt at it. rather than having it in an office space filled with roboticists that understand robots and might not get in the way that somebody who doesn't know what they're doing might. We had this running on a college campus. So this was running live on the floor of Francisco's building in Spain. And so this was being driven during passing periods in a university. So there are many students walking around between classes in major stairwells and over sky bridges. So that we were in the most dynamic kind of environments that we could find to test some of these new dynamic algorithms we have, including TEB and STVL. And we did so for, I think, 23 hours of continuous navigation on 2 different industrial robots to show that it's portable to multiple different platforms. And over the course of these 23 hours, we had no navigation system failures, and we had no direct human assistance. There was a couple of instances of indirect human assistance where the demo autonomy application that we built to test the navigation stack, it would try to go to essentially a couple of different waypoints and then keep going in a circle. And if students were standing on that waypoint, that occasionally caused some problems. So there was some occasional indirect assistance in just having somebody say, "Hey, can you move like half a meter that way so that the robot can achieve its goal to continue moving forward?" So in future experiments, we'll have to make sure that our goal tolerance is a little bit higher.
Okay. Or also you can include into the behavior tree some kind of interaction from the robot itself, so that it says, is the robot?
Yes, yeah, that's a great idea as well. Yeah,
Okay.
yeah. I'm just not, we just didn't quite think about that before the experiment started, and we were pretty close to the deadline for the paper. So
I understand.
It's like, keep going.
Exactly, I understand. And the robots that you used for those experiments were the Tiago and the from Par Robotics and the RB1 from Robotnik, right?
Yeah.
But those robots. Sorry?
There's a couple of robots from Francisco's lab. He participates in the RoboCup competitions. So these are robots he utilizes for those competitions. I don't have any personal experience with either of those 2 platforms, but they look like good robots.
Okay, then I imagine that Francisco, he's the one who ROSified those robots for ROS2, because those robots, they do not come with ROS2 off the shelf when you buy it.
Yeah, don't quote me on this, but I believe the RB1 we were running ROS2 directly on it, that it was running 1804, so we were able to install ROS2 on it, install the navigation stack, and have that running. At the time of this experiment, we were running ROS2 Eloquent, was the most recent distribution. On the PAL robot, I believe it was running 1604, and we couldn't get PAL to assist us in any way for ROS2 support. So we had to an external NUC or some sort of computer, I think it was a laptop, on the base, and then plugged into the back and had that actually running the navigation stack, and then just giving the command velocity topics and getting odometry and stuff back from the robot computer itself. So one of them had ROS2 running directly on it. The other one, it was ROS2 indirectly-ish.
Yeah. Okay. Yeah, like a kind of bridge between the ROS1, which was running
he had built a custom ROS1, ROS2 bridge. I forget why we needed a custom bridge versus the existing bridge, but yeah, we had a custom bridge for some reason.
Yes. Okay, you mean the official bridge in ROS2, ROS1 to ROS2 bridge. It was not that one.
We didn't use that.
You didn't use
I think they were saying with the QoS settings and reliability of like high frequency, large topics like point clouds were causing some issues. So he had created some custom bridge that bridges one topic individually. Then we had many instances of this bridge for the different topics that were giving us problems.
Yeah, makes sense. Can we find this code in somewhere on a Git?
Yeah, if you check out the paper, I don't know the URL offhand. Sorry,
I will put it. Don't worry.
The paper, there's a link to it. Yeah.
So on the paper, on the paper itself, you can find, this is for the audience, okay, because they maybe want to try themselves or see what you have done. So audience there, ROS developers, I'm going to put the link for that on the show notes. Okay, great. And then let me just finish, because we have covered, I'm checking here my questions, but I see that you have answered already many of them, so I'm skipping them. And then let me ask you one final question. So what is lacking ROS2 Navigation Stack to be using commercial products?
Yeah, so I think the major barrier right now is ROS2 itself. With dashing, that was the first LTS distribution of ROS2 available in 1804. There were still a variety of problems. Things were slow, not necessarily discovering very well. Especially the default GDS vendor was not necessarily acting the way that one might expect if you came from ROS1, where things just kind of work. You had to really work to get your performance up, and had to work to figure out all these kind of problems. And so it hits a point where very quickly people just say, this isn't ready yet, moving on. And Eloquent came out then, 6 months after, and was, in my opinion, actually a very, very significant improvement in reliability of ROS2. System started to bring up very quickly within a couple of seconds versus, unreliably, maybe it discovers all the servers within a minute, maybe. So Eloquent made a huge improvement in reliability there. And Foxy is now the first LTS distribution containing those improvements, and also including more DDS vendors as tier 1 supported, including Cyclone DDS, which I find to be the best DDS implementation that currently is available. And but there are still some problems. ROS2 is hard. Like, I'm not going to say that it's not. If you come from ROS1 and you don't have a external C++ background before working with ROS, you're going to have some learning to do, and it's going to be a little bit of a learning curve. So I think that's one of the biggest barrier to entries there, as well as still some performance problems with large topics like point clouds and laser scans and images and things like that. So those are still some of the problems going on in ROS2 itself. I will say that I think you can get anything working at this point in Foxy. I have no doubt that any competent engineer can make it happen. It's going to require more effort on your part. And I think that if you're waiting to move to ROS2 until that effort level drops, then you're just never going to move to ROS2, and you're going to have some problems just because documentation always lags behind development, and we're so focused on development right now that there's more effort being put into documentation. But if you're waiting for a step-by-step guide to fix these problems, you're not going to get it until ROS1 literally goes out of support, and you just can't wait that long. So you just need to kind of buckle up and figure it out. But within the Navigation 2 stack directly, building on top of ROS2, we have some problems with regressions whenever ROS2 has regressions or a DDS vendor has regressions, and that does cause problems that we have to work through on occasion. But in terms of the algorithms and the framework and the actual Navigation 2 system itself, I find fewer and fewer problems that would make me not put it into a commercial product today. I think the biggest one is documentation, so that people can just configure it and don't have to read the code. That said, commercial users, I'm kind of expecting the commercial users are going to get, digging into the code a little bit. But documentation definitely needs to be improved, I believe, as well as kind of professional support. There are currently no organizations that give professional support services towards a lot of these ROS2 projects. So things like Navigation 2, for instance, there's no kind of like consulting company or something that might help companies build custom solutions for this, which I think might be a stopper or a barrier for some large corporations. But otherwise, the algorithms are the original algorithms for Navigation 1, so all the solutions you expect that to be working on will work here. We have more algorithms coming. We have more that have been ported over to ROS from ROS2. So I think, like I said, less and less every day for reasons you can't use it.
Oh, amazing the job that you are doing. Let me just tell you that we are about to launch in our academy a course about setting up the ROS2 navigation stack. It's going to be released next week, so maybe we can help in this thing into providing some practice to the people who want to try that. So it's going on.
Yeah, definitely. Yeah. Just let me know. I'd love to chat about. One of my big tenets is I'm very lucky at Samsung to have a large degree of autonomy to be able to work on these kinds of things and make decisions that are both in the community's best interest, but also in Samsung's best interest of getting more users on ROS2, so there's better support for the different projects that Samsung internally is using ROS2 for. So I can really engage with a lot of companies and help them collaborate in the Navigation 2 system or within the ROS2 system itself. So
amazing, great.
Yeah.
definitely.
Love,
So I'll take your
love to
word.
help you contribute or help others contribute so
Yeah.
that things are better, faster, stronger for everybody.
Great. I think that this is the perfect ending for this. So thanks a lot for coming again to the show, Steve. Thank you very much, and congratulations for the amazing job that you are doing in ROS Navigation Stack and ROS2 in general. Thank you.
Yeah, thank you. Appreciate it.
And then before finishing, I would like to remind you that our goal, the goal of this podcast, is to achieve the 10x increase in the number of listeners. And how can we achieve that? Well, only with your help. So if you like the podcast, please help us reaching that goal. How you can do it? Recommend to your colleagues, give us 5 stars on iTunes or Stitcher, iTunes or Stitcher. You can also listen to this on Spotify. But, well, that's it. That's all for today. So see you next week with a new lesson from the experts. And until then, keep pushing your ROS learning.